Stoichiometry is going to be a very important part of this course, and essentially it involves canceling out units till you get the units that are desired. So this is a practice that's going to be utilized a lot throughout this course and throughout the general chemistry sequence. So I thought I would take this opportunity to go over some practice problems. So here's one practice problem here. We're given the following chemical equation. Sodium phosphate reacts with 3 silver nitrate to give you silver phosphate and sodium nitrate. Notice the equation is balanced. The thing that you look at when you're doing a stoichiometry problem is that you are given a balanced chemical equation. Once you're given a balanced chemical equation, you can start to use the different relationships. Remember one definition of the mole? One definition of the mole is it's the coefficients of a balanced chemical equation. Having said that, for every 3 moles of silver nitrate that react in this reaction, it will react with 1 mole of sodium phosphate. For every 3 moles of silver nitrate, you'll be given 3 moles of sodium nitrate. For every 1 mole of sodium phosphate, you'll get 1 mole of silver phosphate, and on. You can derive all these different relationships based on the coefficient that's in front of the chemical formula. So the first problem asks for how many moles of sodium phosphate would be required to react with 1 mole of silver nitrate. In all types of stoichiometry problems, you're given a number, so you want to work with that number. What you're given is 1 mole of silver nitrate. From what you're given, transfer to what you're being asked. You're being asked how many moles of sodium phosphate will be formed. So for every 1 mole of silver nitrate, for every 3 moles of silver nitrate, how many moles of sodium phosphate react? It's going to be 1 mole of sodium phosphate. And then you want your moles and moles to cancel, because that's what stoichiometry is. It is like a dimensional analysis where you cancel out the units till you get your desired units. And the desired units here are sodium phosphate, because you're asked for moles of sodium phosphate. So the answer is 1/3, or 0.33 moles of sodium phosphate are going to react with 3 moles of silver nitrate. This is just using the relationships from the balanced chemical equation. And that is one definition of the mole. So how many moles of sodium nitrite can be produced from 0.50 moles of sodium phosphate? Again, what are you given? You're given 0.50 moles of sodium phosphate. What are you being asked to find? You're being asked to find the moles of sodium nitrate. So start with what you're given. 0.50 moles of sodium phosphate. For every 1 mole of sodium phosphate, we have how many moles of sodium nitrate? We have 3 moles of sodium nitrate. So 0.5 moles of sodium phosphate. The moles cancel out with the moles of sodium phosphate. You are left with the desirable units of moles of sodium nitrate. Your answer, 1.50 moles of sodium nitrate reacts with 50 moles of sodium phosphate based on the balanced chemical equation, where a better explanation would be 1 mole of sodium phosphate gives you 3 moles of sodium nitrate as a product. How many grams of silver phosphate can be produced from 5 grams of sodium phosphate? What are you given here? 5 grams of sodium phosphate. What are you being asked? You're being asked to compute the grams of silver phosphate. So we start off with 5 grams of sodium phosphate. We're being asked to find the grams of silver phosphate, but before we do that, convert this to moles first. So let's convert sodium phosphate to moles. For every 1 mole of sodium phosphate, there is the molecular weight, 3Na plus P plus 4O. You add all those molecular weights up, you get 163.94 grams of sodium phosphate. How many moles of silver phosphate do we get? For every 1 mole of sodium phosphate, we produced 1 mole of silver phosphate. We have its molecular weight as 418.59 grams per mole. So here is the mole-mole relationship, but to get to that mole-mole relationship, we need to convert sodium phosphate to grams of sodium phosphate to moles of sodium phosphate. So the grams and grams of sodium phosphate cancel. The moles and moles of sodium phosphate cancel. The moles and moles of silver phosphate cancel. And you're left with the grams of silver phosphate. The grams of silver phosphate is what we're being asked. So if you put 5 times 418.58 divided by 163.94, you'll get doing that I get 12.77 grams of silver phosphate. If you have 9.44 grams of sodium phosphate, how many grams of silver nitrate will be needed for complete reaction? So what are you given and what are you being asked? You're given 9.44 grams of sodium phosphate, and you're being asked to compute the grams of silver nitrate. So you're being asked essentially if you have 9.44 grams of this, how much of this will react completely with that. So use stoichiometry one more time. We are given 9.44 grams of sodium phosphate. Let's convert this to moles. For every 1 mole of sodium phosphate, we have as its molecular weight 163.94 grams of sodium phosphate. We know that for every 1 mole of sodium phosphate, there's 3 moles of silver nitrate. And we know that for every 1 mole of silver nitrate, there is in 1 mole of silver nitrate 169.87 grams. Probably round that up to 170.01. Grams of sodium phosphate cancel with grams of sodium phosphate. Moles of sodium phosphate cancel with moles of sodium phosphate. Moles of silver nitrate cancel out with moles of silver nitrate. And you're left with the proper units of grams of silver nitrate, which is what we're being asked to compute, how many grams of silver nitrate. So doing that computation, we will get of silver nitrate. So note here, I first converted the sodium phosphate to moles, and then I used my mole-mole relationship to configure out how many moles of sodium nitrate react with the moles of silver nitrate. I got this relationship from the balanced chemical equation, and then I converted that moles of silver nitrate to grams of silver nitrate. I made sure all my units cancel out, and my final answer is 29.34 grams of silver nitrate. When 25 grams of silver nitrate are reacted with excess sodium phosphate, 18.7 grams of silver phosphate are produced. What is the percentage yield of silver phosphate? The first thing you want to ask yourself is this question. This is how much it is produced. So is that your actual yield or your theoretical yield? This is your actual yield. So this is how much you actually got when you perform the reaction. The theoretical yield is determined based on stoichiometry. So all the previous problems give you the maximum amount that can be produced. Obviously, we will never reach the theoretical yield. We'll only get the actual yield. The reason why is simply because, for some reason, some of the precipitate or some of the solid may spill. Some of the solid may stick to the filter paper when we filter out the precipitate. Some of the precipitate may just evaporate, or some of the whatever human error occurs. We're not robots. Let's see how much of this silver phosphate we can actually produce based on stoichiometry. So we start off with 25 grams of silver nitrate. Let's convert to moles of silver nitrate. 1 mole of silver nitrate has how many grams of silver nitrate? You can look that up. Add the molecular weight of sodium plus N plus 3 times oxygen. And what is the mole-mole relationship between silver nitrate and our product, silver phosphate? 3 moles of silver nitrate, there is 1 mole of silver phosphate. And we know that 1 mole of silver phosphate has how many grams of silver phosphate in that 1 mole? 418.58 grams are in 1 mole of silver phosphate. 3 times the molecular weight of Ag plus P plus 4 times the molecular weight of oxygen. Looking to see our units canceling out. Grams of silver nitrate cancel with grams of silver nitrate. Moles of silver nitrate cancel with moles of silver nitrate. Moles of silver phosphate cancel out with moles of silver phosphate. And on your calculator, you'll put 25 times 418.58 divided by parentheses 169.87 times 3 close parentheses. This is our theoretical yield. This is how much we can maximally produce with excess sodium phosphate. Notice here we have excess sodium phosphate, which means that this reactant, silver nitrate, is your limiting reagent. And this is an excess, so this will be all gone. We'll still have a remainder of this reactant. And this limiting silver nitrate with this excess sodium phosphate produces this much silver phosphate. But based on stoichiometry, if you have 25 grams of silver nitrate, you should get this much. As we stated before, we're not robots, so there's going to be some imperfections. So how much is our percent yield? Percent yield is how much we actually got, our actual yield, 18.7 grams, divided by how much, if the reaction went 100% to perfection and we're robots, how much we should get based on stoichiometry. And that is 20.5 grams. I'll just use it to 3 sig figs. And this is a percentage, so whatever percentage we get, we have to multiply it by 100 to get to the units of percent. Remember, grams canceled. A percentage has no units. It's just a percent. So how good or how efficient we are in this reaction? This is 91.2% is your percent yield. So that's pretty good, a good yield. We were expecting 20.53, we'll never get it, but we actually got 18.7 grams, so we're 91.2% efficient in this reaction. Let's do another practice problem that involves the application of stoichiometry. Here we're given this equation. Potassium permanganate reacts with HCl to give you 5-chlorine, potassium chloride, manganese 2 chloride, and water. So don't forget our nomenclature. Whenever we do a stoichiometry problem is to check to see if our equation is balanced. On the coefficients in front of each chemical formula, this looks like a balanced chemical equation. So let's look at these individual problems. How many moles of HCl are required to react with 35 grams of potassium permanganate? Okay, remember our definition of our mole, or one of our definitions. It's the mole-mole relationship. And what are we given? We're given 35 grams of potassium permanganate, KMnO4. And what are we being asked? We're being asked to calculate the moles of HCl. So we know that for every 1 mole of KMnO4, 1 mole of potassium permanganate has 158.04 grams of potassium permanganate. Now here you're going to use the mole-mole relationship. For every 2 moles of potassium permanganate, we have how many moles of HCl? 15 moles of HCl. Started off with grams of potassium permanganate, we are left with moles of HCl, which is what the problem is asking for. The grams and grams cancel, the moles and moles cancel. So on your calculator you'll do 35 times 16 divided by 158 times 2. Usually what I'd like to do is 35 times 16 divided by parentheses 158.04 times 2 and close the parentheses. 0.77 moles of HCl, I'll round it up to 2 sig figs, and we'll get 0.8 moles of HCl reacting. Move on to part B. How many Cl2 molecules will be produced using 3 moles of potassium permanganate? What are we given? What are we being asked? Given 3 moles of potassium permanganate, 3 moles of KMnO4, times, we know that for every 2 moles of potassium permanganate, have 5 moles of Cl2. We know that for every 1 mole of Cl2, we have 2 times 6.02 times 10 to the 23 molecules of Cl2. 1 mole of Cl has 6.02 times 10 to the 23. Then 1 mole of Cl2, you have to multiply it by 2. Okay? So 1 mole of Cl will have 1 mole of Cl2 will have 2 times that. So the moles and moles of KMnO4 cancel, the moles of Cl2 cancel with the moles of Cl2. So on your calculator you'll do 3 times 5. 3 times 5 is 2 times 6.022 exponent 23 That's Avogadro's number. And that is what this equals to. And you're going to divide that by 2. And you get 9.03 times 10 to the 24 molecules of Cl2. That is the answer. If you wanted to 2 sig figs, then you would just go 9.0 times 10 to the 24 molecules of Cl2. Produce 35 grams of MnCl2 product. What mass of HCl will need to react? So what are we given? What are we being asked? Being given 35 grams of MnCl2. Convert this to mole. 1 mole of MnCl2. Do that, you'll get approximately 125.01 grams of MnCl2. We know that for every 2 moles of MnCl2, there's 16 moles of HCl. 2 moles of MnCl2, there are 16 moles of HCl. We know that for every 1 mole of HCl, we have about 36.01 grams of HCl. Pull out your units. We know that grams of MnCl2 cancel with grams of MnCl2. Moles of MnCl2 cancel out with moles of MnCl2. Moles of HCl cancel out with moles of HCl. And when you do this on your calculator, 80.7 grams of HCl. So you're going to need 80.7 grams of HCl and however much of this we have to calculate that. You're going to need 80.7 grams of HCl to, at the bare minimum, generate 35 grams of MnCl2. 8 moles of KMnO4 potassium permanganate react. How many moles of water will be produced? Okay, water is also your product. KMnO4 is your reactant. You've given, and then it's what you're being asked. You're given 8 moles of KMnO4. How many moles of water will be produced? So we know that for every 2 moles of KMnO4, there is 8 moles of water. The moles of KMnO4 cancel with the moles of KMnO4, and you're left with 8 times 8 divided by 2. 64 divided by 2 is 32 moles of water. 2 moles of water will be produced. You react with 8 moles of KMnO4 based on the relationship, mole-mole relationship, the coefficients of a balanced chemical equation. Maximum mass of Cl2 that can be produced by reacting 70 grams of KMnO4 with 15 grams of HCl. So we have KMnO4 and we have Cl. We need to know which one of these reactants is going to be the limiting reagent and which one of these reactants is going to be the excess reagent. So here we have mass LO2 produced utilizing all KMnO4, scenario 1. So we know that 70 grams KMnO4, our first reactant, grams of this and 15 grams of that, each of this will be produced. One of these is going to get eaten up first. One is going to be in excess. MnO4, the molecular weight of KMnO4, that based on our mole-mole relationship, for every 2 moles of KMnO4, there is 5 moles of Cl2. 2 moles of KMnO4, 5 moles of Cl2. And for every 1 mole of Cl2, there is 70.01 grams of Cl2. So this is how much Cl2 product is produced when all of this is used up. Putting that in our calculator, realizing that the grams of KMnO4 cancel, the moles of KMnO4 cancel, and the moles of Cl2 cancel, 5 grams of Cl2. Now this is the amount that's produced if all of the KMnO4 react. Let's look at the mass of Cl2 produced. All the 15 grams of HCl is used up, utilizing all 15 grams of HCl. We have 15 grams of HCl. Know that for every 1 mole of HCl, we have 36.01 grams of HCl. Know that for every 16 moles of HCl, 5 moles of Cl2. 16 moles of HCl, we have 5 moles of Cl2 produced as product. Know that for every 1 mole of HCl, for every 1 mole of Cl2, we have 70.01 grams of Cl2. Grams of HCl cancel with grams of HCl. The moles of HCl cancel with one another. The moles of Cl2 cancel with one another. And you're left with grams of Cl2. So 15 times 5 times 70 divided by parentheses 36.01 times 16 close parentheses. We're left with 9.11 grams of Cl2. This is how much Cl2 is produced if all of the 15 grams of HCl is used up. Maximum mass of Cl2 that is actually produced is going to be 9.11 grams of Cl2. See, 15 grams of HCl are going to get used up first because this is the limiting reagent. 15 grams of HCl is going to produce 9.11 grams of Cl2. This 70 grams of KMnO4 is going to produce 77.5 grams of Cl2. KMnO4 is your excess reagent. You can never make more than what your limiting reagent allows you to make. So in this case, by reacting 70 grams of KMnO4 reactant with 15 grams of HCl reactant, all going to get used up, and that sets the limit on the amount of Cl2 you will make. And based on stoichiometry, you will produce 9.11 grams of Cl2.